Hello friends, this is Anita Rai, and in this presentation video we'll be deriving Bernoulli's equation by balancing a force on a fluid element that is flowing through a pipe. Well, I'm pretty sure by this time you all are aware of how important this Bernoulli's equation is while solving the problem related to fluid flow. And there are numerous ways to derive this equation, but for this presentation we'll be deriving it by balancing a force on a fluid element as stated by the topic, and for that we'll be using concepts such as Newton's second law of motion and most importantly Euler's equation of motion. So these are the outlines of my presentation. Firstly, before deriving the equation, we will be considering some of the assumptions made to derive this equation, and then we will be deriving Euler's equation of motion, and then finally integrating it, we will be deriving Bernoulli's equation and state what it is, and lastly reference. So these are the assumptions that are used in deriving this equation. The first assumption says that the fluid flow is irrotational, or they are on the same streamline. So what this statement is telling is that if suppose a fluid is flowing from location A to B, then those fluid particles, they flow in this same streamline, just as shown in this figure, and they do not rotate in their own axis. The second says the fluid is incompressible. Incompressible meaning when we exert pressure to the fluid, then their volume doesn't change and it remains constant. So when the volume remains constant, their density also remains constant. And third one says that the fluid is idle, which means that the viscosity of the fluid is 0. And the last one says that the flow is steady, which means that the flowing parameters such as velocity, temperature, pressure remains constant at every point and they do not change with respect to time. So as I said earlier, first we will be deriving Euler's equation of motion, and then integrating it we will be deriving Bernoulli's equation. So for that, let us consider a fluid element that is flowing through this pipe. And for that, consider that the fluid element has area dA and length of ds. Now consider at this side this pressure P is acting. So what do you mean by pressure? Pressure is equal to force per unit area, right? And we can write pressure force as pressure times area. But here at this side we consider area as dA. So the pressure force acting at this side is PdA. And this is the direction of the flow of the motion. And we know that at the other side there is always one force that opposes or acts against the motion of the fluid. So here if pressure is P, then with respect to distance, pressure here is changed. If suppose this is the first pressure, then with respect to distance, pressure here is changed. So pressure here is P plus del P by del S times ds. But we know that pressure force is equal to pressure times area. So this is the pressure force that is acting against the motion of the fluid. Now to talk about the third force, it is due to the gravity. As you can see here, the weight is acting downward. So what is weight? Weight is equal to mass times gravity. And we know that density is equal to mass per unit volume. So mass can also be written as rho v. So as you have seen, we have written rho v in place of mass and g as it is. But we also know that volume is equal to area times length. So area dA and length is ds. So finally the value of weight force is rho g dA ds. So in Euler's equation of motion, we basically consider three forces, that is pressure force acting towards the motion of the fluid, the other pressure force that is acting against the motion of the fluid, and lastly the weight force due to gravity. So as mentioned earlier, in Euler's equation of motion, we consider three forces, that is force due to pressure, we have two, that is pressure force towards the flow of motion, and the other pressure force that acts against the motion of the fluid, and lastly the force due to gravity, that is weight force. Now consider this theta is an angle between the weight of the fluid element and direction of the flow of the motion of the fluid. So here at the angle adjacent side we can write cos theta, right? But we know that the weight of force acting here is rho g dA ds. So we can also write rho g dA ds cos theta at the angle adjacent side here. So our next step is to find the resultant force. Here we consider that the force that is acting upward is positive and those forces that are acting downward are negative. So here we can find the resultant force as P dA as positive as it's acting upward, and minus rho g dA ds cos theta as it's acting downward, and minus P plus del P by del S times ds times dA. But we also know that force is equal to mass times acceleration. So what this concept is trying to say is that the resultant force must be equal to mass of the fluid element and acceleration in the direction of the flow of the motion. So our next step is to find the value of mass. We know that the density is equal to mass per unit volume, so mass is equal to rho v. And we also know that volume is equal to area times length, that is dA times ds. So finally we can replace the value of mass as rho dA ds. So as explained earlier, our resultant force must equal to the mass or weight of the fluid element times acceleration in the direction of the fluid flow. So what was our resultant force? Our resultant force was P dA minus P plus del P by del S times ds times dA minus rho g dA ds cos theta, which is equal to mass of the fluid element, that is rho dA ds times as, that is acceleration. So if you simplify this equation, you can see here minus P dA here also. So we can write P dA minus P dA. So what remains? Minus del P by del S times ds times dA minus rho g dA ds cos theta, which is equal to rho dA ds times as. So here P dA minus P dA gets cancelled. So what remains is minus del P by del S times ds times dA minus rho g dA ds cos theta, which is equal to rho dA ds times as. So let this be our equation 1. Our next focus is to find the value of as, that is acceleration. So what do you mean by acceleration? We know that acceleration is equal to dv by dt, that is rate of change of velocity with respect to time. But we also know that velocity is equal to ds by dt, that is rate of change of distance with respect to time. So velocity is the function of s and t. So here we use partial derivatives to represent dv by dt, and instead of this we will be replacing it with delta v by delta s times ds by dt plus delta v by delta t times dt by dt. Dt gets cancelled, so in place of ds by dt we can write velocity, right? So what do we get? We get delta v by delta s times velocity plus delta v by delta t. But if you remember, we have assumed that the flow is steady, which means that the rate of change of velocity with respect to time is 0. So the derivative of dv by dt is 0. So here the value of dv by dt is also 0. So finally what do we get? The value of as, we get velocity times delta v by delta s. So if you put this value in equation 1, what was our equation 1? This was our equation 1, right? So as you can see here, this is our equation 1, and I have already substituted the value of acceleration. Now if you divide this equation by rho dA ds, that is the value of the mass or weight of the fluid element, then here if you divide this, ds dA gets cancelled, so what remains is rho. So we'll get minus del P by rho ds minus here rho dA ds gets cancelled, so we will get minus g cos theta, which is equal to rho d ds gets cancelled, so what we'll get velocity times del v by del s. Now if we rearrange this equation, like putting this equation here in the right hand side, then this will become positive. So this is what we have done. Then we'll get del p by rho del s plus g cos theta plus velocity times del v by del s is equal to 0. But as shown in the figure here, you can see that the length of this triangle is ds and height is dz, and the angle between them is theta. So we can write cos theta as dz by ds. Now if we substitute the value of cos theta in the above equation, what do we get? We get delta p by rho ds plus g. So in place of cos theta, dz by ds plus velocity times delta v by delta s, which is equal to 0. Now if you look carefully, they all have got similarities, that is del s. So simplifying it, we'll get delta p by rho plus g dz plus v dv is equal to 0. So finally we get Euler's equation of motion, which states the relationship between density, pressure and velocity of the fluid. But our work is not done yet. Our work is to derive Bernoulli's equation by integrating this Euler's equation of motion. So in the next step, you can see this is the Euler's equation of motion. Now we will integrate it to derive Bernoulli's equation. But before that, we have made a consideration that the flow is incompressible, in which volume doesn't change due to pressure and density remains constant. So before integrating, we will be taking out constant. So the constant here is rho and g. So integration of dp will get p, integration of dz will getting z, and integration of v dv will getting v square by 2. So finally what we get, will get p divided by rho plus gz plus v square by 2 is equal to constant. Now if we divide this equation by g, then what we'll get p divided by rho g plus g gets cancelled, so z will remain, and we'll get v square divided by 2g is equal to constant. So finally what you are seeing, this is the Bernoulli's equation. So p divided by rho g is the pressure head, v square divided by 2g is the kinetic head, and z is the potential head. Now if we state this Bernoulli's theorem, it states that in a steady ideal flow of an incompressible fluid, the total energy at any point, which total energy, the sum of pressure energy, kinetic energy and potential energy at any point of the fluid, is always constant. I repeat, in a steady ideal flow of an incompressible fluid, the total energy, that is the sum of pressure energy, kinetic energy and potential energy, is always constant at any point of the fluid flow. So this is the very equation that we have derived, and this is the Bernoulli's equation. So this is the reference that I referred. And lastly, thank you, and I hope you have learned how to derive Bernoulli's equation by